Okay, so this webinar is meant to be specifically about the ISO test as opposed to the NFPA, which our past webinars have been about, and there are some significant differences. But essentially, they both say the same thing, that the hold time is determined by the door fan. And as some of you may know, the door fan test is also an ideal way to measure the enclosure leakage to estimate the peak pressure. Both standards require that the hold time, the concentration is held at 85% design for 10 minutes, and there are sections in there that ask that the test be repeated annually. On the next slide here, we're talking about the 2006 version of ISO, which was the first time that some major changes have been made from the 2006 version. A lot of the changes that had been made to it for descending interface in particular have vastly made ISO more conservative. The first one is that the wide interface has decreased the hold time by at least 25%, in some cases almost 50%, because it simulates an interface which was thought to be wide, and we've since found that's not the case. It's a lot more conservative than it has to be. And also, the requirement for protection got raised up to 90% of the enclosure height. Both of those made it extremely conservative and so on, and required a lot of extra tightening. In some cases, countries such as Australia didn't accept the 90% of enclosure height as a forced minimum protected height. But in most countries in Europe, the 90% of the enclosure height is still being required, which makes it extremely tight for a descending interface. There's another important change, which is actually a mistake in E 3.4.2, which is pretty important, and it should read that F equals 0.15. It actually says it's equal to 0.5, which makes the whole section irrelevant. So it's a clear mistake. If we go back to the 2000 version, we see that it should equal 0.15, and that becomes critical when we are when we're measuring enclosure leakage distribution, which is one of the important features that enables us to get a more accurate and often longer retention time prediction, as we will go into in a lot of detail later on. There's also a section in 7.4.1 that says the enclosure must have sufficient strength to contain the agent discharge. So what we know about this, we've learned from a 4-year research project which involved most of the major manufacturers and was carried out at FIKE in Missouri, and I was involved in it for roughly about 5 years or so. And there's me sitting at the table collecting a bunch of data and so on. And this is Bob Whiteley from Wormold, who is the head of the ISO committee. So just about every country, every major company was involved in this project. The original purpose of the project was to get a more accurate idea of what peak pressures were under test conditions, and moreover to accurately compare the peak pressure values that we were getting with the door fan measurement of enclosure leakage. These are the different agents that were discharged. As you can see, pretty much all of the major agents that are being used. And these are the different years that the testing occurred and the number of discharges that took place. And you'll notice that the research project ended in 2007, and at that point we had several million pieces of data, and it took us several years to get that correlated. There were two things we were looking for. One was peak pressure, the other was the shape of the descending interface. This is a table showing the various research projects that were undertaken to determine peak pressure in enclosures, and I went back, read all the literature that I could find, and this is what I came across. In order to depict enclosure leakage as it affects peak pressure, we had to come up with a simple way of evaluating one enclosure to the next, and we came up with the idea of the leak to volume ratio. So the idea is that when the enclosure volume doubles, the leakage area has to double to maintain the same peak pressure. So once you get a value of the leak to volume ratio for one enclosure, it applies to all enclosures, no matter how tall, wide, or indifferent that enclosure is, assuming that the discharge characteristics when the agent is released are the same. And typically it's a valve which opens 100% open immediately, and the agent flows down the pipe, the resistance in the pipe, which will be the same no matter what size of enclosure that we discharge into. The only time that will vary is if we have a pressure regulating valve, which we also tested as well, and I know that Tyco, Siemens, and Fike all have pressure regulating valves. They all seem to have a similar characteristic, and they also have the leak to volume ratio, which is characteristic. So we get a pressure curve that looks like this with an inert, where we have a very short-term pressure spike that leaps up when the valve opens instantly and then drops off exponentially. This particular graph shows the range of inert peak pressure readings that we got over a wide range of peak pressures. One of the problems that we discovered with the previous research is it was all done around one leak to volume ratio, if you will. So no matter how many discharges we did into that enclosure, we pretty much always verified the 1 point on the curve. What we did that was different here was that we did it over a wide range of enclosure leakages, all the way from, let's say, an 8-minute retention time to a 30-minute retention time and different enclosure heights. So we carefully programmed the peak pressure releases so they would correlate with what would effectively be different hold times. So this hadn't really been done before because people were looking at peak pressures on their own and not trying to correlate them with the hold times, but peak pressures and hold times are related, so we have to look at it in this way in order to get what we call the characteristic shape of the curve. And the reason why that's important, we just flash back to this curve here. The shape of this curve is some kind of oddball exponential power, and this is the shape of the curve that we got, and the dashed lines were the shapes of the curves of all the existing peak pressure formulas at the time, and they all had the same characteristic, which was that they used a square root relationship, and it's not a square root relationship, so you could see, just like the clock that's not working, it's right at least one time a day. In this area of around about 1250 pascals of peak pressure, we get some kind of a correlation with the data, but what's really important here is we get a really wide divergence in the area of interest, which is where we tighten up the enclosures in order to get the hold time that we want. So this and this are the two areas of interest, and you can see here that we can have as much as a 200 or even a 400% error in the peak pressure formulas. So what that means is that the existing venting formulas that we are using and continue to use are out by 200 to 400%, meaning we will get 2 to 4 times as much peak pressure as the existing equations tell us that we're going to get. So here, a little bit out of order, we have the peak pressure curve for a typical inert, and this is the peak pressure curve for a pressure regulating valve, In this case, it was pro-inert, and you'll notice that it comes up to a certain value, and then it kind of maintains a more or less steady period over the discharge time. So what that does is it reduces the peak pressure in cases like that by about 50%. And I think that's the way the industry is starting to go at this point. The other big surprise in this research project was that halocarbons have similar but different characteristic curves. And in this case, this was one of the few formulas we had for halocarbons, and we'll notice that also these curves are vastly different as well. What's different about the halocarbons is that if we had any formulas at all, the formulas we had were over-predicting peak pressure instead of under-predicting peak pressure. So we have just the reverse problem. But we did find that once the enclosures were tightened down to the level that they need to in order to maintain concentration, that we can have almost as much peak pressure with some halocarbons as we do with the inerts. The other big surprise was that most of the halocarbons produced a negative pressure spike in addition to a positive pressure spike. So here we have FM200 essentially going negative and then going positive. The different curves here show the different enclosure leakages, and as the enclosure gets tighter, the peak pressure, the negative peak pressure and the positive peak pressure, it's not quite linear with enclosure leakage, but it's reasonably close. So we can see here with the most leakage we have the smallest pressure spike. And for halocarbons, the interesting news was also that humidity affected the results a lot, so that for halocarbon, if we were to discharge at a very, very dry humidity, then we'll get a huge negative pressure spike. If we discharge at a very high humidity, we get almost no negative pressure spike at all. And this is because with a halocarbon, the negative pressure spike is caused by, essentially you could say, evaporation, where the agent starts as a liquid and then flashes to a gas and causes cooling. And when we have a very, very high humidity, as you know, we have very little cooling, so we all know that from our own personal experience. So someone was asking, will there be a pressure regulating valve correction in the software at any time? There is one there right now, and yes, it does make a lot of sense. But if you choose Pro Inert right now, you will essentially get the proper peak pressure curve for any of the pressure regulating valves. And in my discussions with Siemens and Tyco, the data that I have so far indicates that the values for Pro Inert for peak pressure will be the same, and in future versions of the software we'll have the trade names of those agents in there. But for the time being, if you're using any inert pressure regulating valve, then use the Pro Inert curves, and they will give you as good a result as we have information at the present time. As far as inerts are concerned, we can essentially ignore humidity. There's virtually no effect whatsoever. So here we see the reason for the big, actually not so much the reason, but the effect of the negative spike. Here we have FM200 and Novak with a very, very rapid drop in temperature over about a 5 or 6 second period that's due to cooling, and then it drops off. With the inert, in this case IG55, we have a little bit of cooling that goes on in the room, but nowhere near the slope of this particular curve, and don't get any appreciable or observable pressure spike, negative pressure spike because of it. So here we have Novak again with the negative drop in the first, what is that, 5 seconds or so. not even, about a two-second window there where we have the maximum amount of mass of agent going into the room, the maximum amount of cooling. It very quickly reverses itself, and so by the time 4 or 5 seconds are up, it's gone through zero, and then we get a positive pressure spike, which is produced by the nitrogen blowdown in the tank. This is in pounds per square foot. 1 pound per square foot is about 50 pascals, so that's around about minus 150 pascals in this particular diagram. Here we have HFC 125, again, and halocarbon or chemical agent. A very small positive pressure spike here, the characteristic negative, the characteristic positive. Seems like HFC 125 has pretty equal negative and positive spikes, and each one of these agents are different, and they're different for different humidities, and our software takes care of all of them. So as far as peak pressure design is concerned, the good news is that we just completed the first version of our designed software addition to Fantastic Integrity, and I'll just be previewing it earlier so you can take a look at it. And some of the values that need to go into that in order to do the evaluation in the design phase is to specify an enclosure strength, which essentially determines the necessary leak to volume ratio, which is based on the agent, the type of valve, the rate of discharge, and so on, and will size the vents. Now, here we say if needed. The European design philosophy says that we do not use enclosure leakage as a way of venting pressure, so you can say that they're just about always needed, at least just about always need a pressure vent. So this is the section in Fantastic Integrity that shows the peak pressure. Let's see, what is the agent that we have here? This would be an inert agent in this case, where it's only showing positive peak pressure. So we show the peak pressure evaluation and also the hold time in the same software package. This particular webinar was not really meant to be a detailed training course on how to use Fantastic Integrity. It's more of an overview. Over the next few weeks, we're going to be having level 1, level 2, level 3 training courses that will go into more details of exactly how the software should be used. But most of this is covered in our training course and training manuals on that. This is a slide of a dual-acting pressure relief vent. So whenever we're installing a halocarbon, these are the most efficient vents to install because they allow the pressure to be relieved in both directions. This shows one of our latest products, I guess, which is what we call the contra-rotating fan, which is 2 of our high-power fans connected together, and it has the blades going in opposite directions, which is something that we use in order to measure pressure relief vent performance up to 500 pascals and about 4,000 or 5,000 CFM. This is the hold time presentation from our software. So we're just going to jump over here to the ISO 2000 edition had what we call a sharp interface, which said that there was, as agent ran out of the enclosure, there was air above and agent below, and there was no essentially thickness in the descending interface. The 2006 version came in with what they call the wide interface assumption, and it said as the agent runs out, the interface continues to widen until it extends from the top of the enclosure to the bottom. We found out it's not actually the case, so this is the wide interface here. It performs more like this. I know the difference might be a little bit discrete, but you'll notice that the height prediction for the wide interface here is much lower than it is for the thick interface. And we've made changes to the ISO standard. These things take years, and we've done numerous presentations to the committees. The wording has all been changed to put in the new thick interface, but it's we have a standard right now which is, as most of you know, very, very conservative for predicting hold time, and these changes will be reflected in the new version of ISO when it comes out. So here we have a different kind of graphical representation of the sharp interface, the wide interface, and the thick interface. What it amounts to for the thick interface, which is how the agent actually performs in the enclosure, is the interface goes to its characteristic thickness and stays there regardless of height, and I'll be showing that. This is what an interface actually looks like, and I won't spend a lot of time on this. It's a little bit arcane, and these are the appearance of the interfaces for the two inerts and the halocarbons, and these are the characteristic thicknesses that you can see of the interfaces. You'll notice that the halocarbons have interfaces which actually are around about 1/2 meter thick, and the inerts have interfaces which are about 1 meter thick, and that's all reflected in the new standards. And IG 100 essentially has no interface formation at all. IG 55, when we look at height versus hold time and the data that we took, the ISO standard is here, showing very, very conservative, showing very, very short retention time. NFPA is over here, and the truth actually is right in the middle there somewhere. This graph shows it in a different way, the degree of conservatism, I guess, with NFPA being not conservative at all, and the proposed hitting it right on the nose, and in this case the ISO current being quite conservative. When we look at halocarbons, the existing equations that we have for the sharp interface are actually pretty accurate. As we see here for Novak, NFPA or the sharp interface is a little bit a negative conservatism, which means optimistic, and here we're showing the ISO equations at 0.85 of initial concentration of being extremely conservative. Now, this is in addition to the fact that we're still looking at a worst case, so in actual fact, this conservatism of 35% might be 60, 70, or even 80% conservative, because the leaks are never in exactly the worst case, or seldom. And here we show FM200 with the sharp interface shown here and the data almost right on top of it. So this indicates that the sharp interface formulas are actually very, very close for FM200. The assumption here is that we're always going to be installing a pressure relief vent, and the more accurate prediction that we can make of it, the smaller vent that we can install. If we always install the largest possible vent, it can be very costly. So let's just take a look at that. The first one is to be realistic about the enclosure pressure limit. This is the only study that I've been able to find on enclosure strength, and it's in the public domain, so we're using it. The table's in pounds per square foot, and the figures that I use for a standard 2x4 wall is 250 pascals, 2x6 wall 500 pascals, a 2x8 wall 750 pascals, and 1,000 pascals for reinforced concrete or concrete block walls that have reinforcing in them. A concrete block wall that doesn't have reinforcing in it is not much stronger than a 2x4 wall, and they can actually crack relatively easily. So here we call this comparing agents, but in effect what it shows that the inert agents require a lot less air sealing. Here, this is the total leakage in total square inches to get the same retention time. But we actually have, for the same retention time, we actually have very similar peak pressures as you can see here, which is interesting. So we've got 507 pascals for the inert, 386 pascals for Novak. Very similar. So there's not a huge difference when you compare agents, but that will be a determining factor for choosing the size of the vent. The other point that I often use is the fact that we don't necessarily have to install purpose-built pressure relief vents. Often what happens is that all of the HVAC system is often isolated with vents that close, and by simply changing the timing on the closure of these vents, we can provide a pressure relief vent through the existing HVAC ductwork. So essentially you get a free pressure relief vent by changing the timing of the closure of the vents in the HVAC system. And this can be measured with the door fan. You can find out how much, essentially how much venting you're getting with the HVAC system. There are 4 other ways to reduce the pressure relief vent, but these don't have as much effect as you would think. You can put different discharge times into the software and you can see how much difference it makes. I found in some cases where I was to cut the discharge time in half, you would expect to get at least double the peak pressure. But in fact, in a lot of cases, since the cooling increases, it offsets the fact that more massive agent is being stuffed into the room and doesn't give you as much of an increase in peak pressure as you might think. The other is to decrease concentration, which has a small effect. In the case of halocarbons, to raise the minimum humidity, and as we discussed already, the presence of an inert agent regulating valve, which in most cases will have the vent area requirement. I'm just going to bring up our new software package, and hopefully you can see that. So this is the beta version of our software. Under Tools, we'll have a choice called Venting Calculator, and on the Venting Calculator we get a little screen like this that allows us to choose the venting equation. Let's say we choose VDS, standard that we'll be using, in this case ISO, the agent that we might be using, any one of our agents, descending interface, all the various functions that affect venting, and then it will give you, let's see, we hit calculate, and it gives you the size of pressure the size of pressure relief vent area that will be needed in terms of free vent area. The important thing about this free vent area is to test whatever pressure relief vent you're using in order to see how much free vent area it actually has. It's relatively easy to do. I would typically just take it and put it in a big box, negatively pressurize a box, and see at what pressures the vent opens first of all, and to see what vent area it has, and our gauges can be set to EQLA, not EFLA, but EQLA, and that EQLA in square centimeters will tell you what free vent area that vent actually has. Obviously, when it's connected to ductwork and so on, that free vent area will be reduced, so whatever you measure in this box will be the maximum free vent area that you would ever get. But if you're venting right through a wall, then you would get that at least through the vent, and then you have to measure the rest of the vent path. So we won't spend a lot of time working on this, but this is a new feature that will be showing up in your enclosure integrity software when you update it after we've gone through the beta process, which take another couple of weeks, will automatically appear in your software. So let's just take a look at some options to, in this case, increase the hold time. So this becomes relevant when you do a test on an enclosure and you fail, or you may also want to take a look at this in the design phase. And as you'll see, some of the decisions we'll make in the design will dramatically affect the performance of the system. Also, don't hesitate to ask questions while we're going. It gives me an idea as to what you're understanding or not understanding as I'm going. I know for some of you who are new to this, a lot of this might just be totally confusing. Understand that. If you go through the level 1 training, for example, it goes through this methodically. It teaches you the basics and so forth. So this is not really a basic course. It's more kind of an introduction to the overall concept of pressure venting and hold time. So the first one is to specify, or at least take a look at the idea of continuous mixing. Generally, higher concentrations will give you longer hold times, and in order to get continuous mixing, we can either do that by leaving the HVAC running during the hold time, or in a lot of cases we have unintentional continuous mixing just caused by the thermal effects of hot equipment in the room or the cooling fans that are inside the equipment. So here I have two examples. This was done in enclosure integrity. Here we show a descending interface, and everything is the same between these two screens here. A descending interface with an estimated leakage area of 200 square centimeters and a hold time of 5.1 minutes. By changing nothing except going to continual mixing, we got the same concentration, the same leakage area, we almost triple the retention time. Part of this has got to do with the extremely conservative nature of the ISO equations. If we were to increase this initial concentration to 8%, for example, this would jump up to about 25 minutes, because with continual mixing, we're looking at the drop in concentration from 7% to 6%. With descending interface, we're looking at the drop from 4 meters to 3.6 meters. So this is 10% essentially of the volume of the enclosure being lost here. And here we're talking about 1/7 of essentially the volume of the enclosure being lost. And that's one of the reasons why with continuous mixing for ISO, we will always get a substantially longer retention time. And this essentially points to the fact that continuous mixing is extremely favored for any equation or any enclosure being evaluated using the ISO or the EN process, and would recommend that you take a very focused look at continuous mixing, which is often ignored. It's always assumed as a descending interface at discharge, and that's not the case. So this is a very important point. So this continuous mixing can occur because of circulating fans or the AC continuing to run. Again, we're comparing agents, and this will have a lot of effect on the hold time as well. And a third option is extended discharge, which is something that should be considered during the design phase. Often if an enclosure won't pass no matter what, then we simply run the descending interface formulas in enclosure integrity software. we determine what the extended discharge rate is, and we continue to discharge agent at the loss rate into the enclosure so we can hold for any period of time that we want. As long as we continue to discharge at the rate of loss, we'll always maintain our concentration. And the other one is, particularly for small enclosures, is to look at the possibility of reducing the hold time. Both NFPA and ISO specify 10 minutes, but they do say, unless otherwise specified by the authority, generally the authority goes along with whatever the design is, although some of them tend to focus on it being 10 minutes regardless. But particularly for small enclosures, a case could be made for sometimes having only a 5-minute retention time, or even 2 minutes if the enclosure is very, very small. Getting small enclosures tight enough to pass hold time is probably the single most difficult problem that enclosure testers face. The other one is reducing the lower leaks, which, as we'll see in the next example, we have a descending interface with, again, a 200 square centimeter leakage area, a 5.1 minute retention time. And all we've done here is to measure the lower leaks, which ISO allows you to do, and the hold time is more than doubled to 11 minutes. So this is a very important test that we can perform, and how we do that is to, actually, just backing up here, we show here an enclosure that is being tested using a whole room approach. And here the enclosure leakage needs to get down to 15 square inches in this case to pass with FM200, but we can have a total of 30 square inches of leakage as long as the lower leak is a small fraction of the upper leak, and we still get the retention time that we need. So in this case, there's half as much air sealing has taken place, but we've still passed, and that's only as a result of measuring the enclosure leakage distribution and determining that there are not any significant holes in the bottom part of the enclosure that will cause agent loss. One way to do this is to cover the ceiling in plastic, and for any of those out there that have ever done this, it's very time consuming, but it does work. It takes several hours at least to do this. The other way to do that is to have a double fan system and to simply duct one of the fans to the above ceiling space here to neutralize the pressure across the suspended ceiling, and then this fan will be measuring the lower leak, which is put into the equations, and this can be done in about 20 minutes or so. The new gauges that we have a set to zero function, which allows the whole process to be automated, and is by far the fastest and quickest way to do a lower leak test and to get sufficient hold time in these enclosures. You'll notice that the panel system we're using is an aluminum frame panel system. This is for very, very small rooms. We need to use this because they're specially designed with these new square corners to fit right into the corner and be very, very tight so that the panel itself is not leaking at all. And this is a schematic showing how one fan is depressurizing the above ceiling space and the lower fan is measuring the lower leak. And there's another picture of the same thing. The same principle can be used for subfloor only testing, where we pressurize the room with one fan and we have another fan that's on the floor that's measuring the lower leak. So in this case, we're neutralizing the pressure across the walk-down floor, and we've got the vents in the floor sealed off, and it's the same process. We can also use this process as a way of determining the size of the lower leak. ISO allows us to use this as a method of measuring the lower leak. This is taken care of in our level 3 training. Just briefly touch on some design tips. Again, if you've got any questions as we go, I'm more than happy to respond to them. So the first thing is that let's just take a look at these slides here. That the PRV should open early, and all of these PRVs need to be measured to see at what pressure they open. I prefer that they open at around 75 or 100 pascals maximum, so that we start to relieve the peak pressure early. And here we show a graph showing what happens if we relieve pressure at 50 pascals, 250 pascals, or in this case we've got no pressure relief at all. So here our pressure relief vent is opening at 250. It starts to open here, and it causes a bit of overshoot to occur. If we have the same vent opening at 50 pascals, here it doesn't allow the buildup of pressure, and is much, much more effective. Number two is to vent as high as possible. Typically we want to vent in the upper quarter of the room so that as the agent comes in, the air vents out. And it's extremely important to measure whatever vent area we have with your door fan, which you can measure when the vent is installed. And it's the best way to determine whether the vent opens up, and that's part of the testing procedure that we describe in our training course. So measuring vent area is extremely important. In many cases, the vents don't open when they're supposed to. So in this case, this particular vent is only open about 20% at 250 pascals. And a test of the vent in a box or even in the room will show that very quickly. Or the vent can be blocked. So we may have a vent that has tons of area, but it's blocked. It has a rain flap or something that has something in front of it, and it's obstructed in some way. That's why the venting path needs to be measured on a regular basis. And on the same basis, electronic dampers need to be checked on an annual basis to ensure that they will in fact open as designed. And in other cases, for halocarbons, the vents are installed improperly to vent a positive pressure, and there is no positive pressure at all. I guess that's part of the learning process. The software will tell you how much negative venting you need and how much positive venting you need. So hopefully we can solve that one. And the next one is to ensure that the suspended ceiling is properly vented so that when the discharge occurs and the agent's trying to find its way back to the holes above the suspended ceiling, that it doesn't take the ceiling with it. So we have a very simple formula for doing that. That's something that we certainly need to be looking at whenever we're inspecting an enclosure. The next one is to, of course, run the enclosure calculation during the design phase. This is our new venting calculator, which will, in a week or two, will be in all of your hands if you have enclosure integrity, or if you download a free version from our website so that you can do the peak pressure on the whole time evaluation in one place. So I've got a question there where someone says for continuum mixing, the initial concentration must be increased 15% over the minimum design concentration. It says in my slides I show the opposite. Not exactly. This is more true with NFPA because concentration that we have to hold with NFPA and ISO is 85% of design, so that only allows us to lose 15% of our agent. With ISO, because of the 90% of enclosure height, we have to hold 90% of our agent for descending interface. So descending interface for ISO is much, much more conservative. The reverse is true with NFPA, where for a typical enclosure, we have to hold to, let's say, 75% of room height, so we can lose a lot more agent for descending interface. It's not true with ISO. So I was actually surprised to discover that even if we put in a low concentration of agent that the continuum mixing still outperforms descending interface by a wide margin. That doesn't mean that if we increase the agent quantity for continuum mixing, we won't get a longer retention time. We will. So in the example I showed, we had a 7% initial concentration dropping to 85% of that, which I think is about 6%. If we increase the initial concentration to 8%, we would double our retention time. If we increase it to 9%, we'd add another 50% to our retention time. So that's the point there. So as far as enclosure design is concerned, increasing the agent volume increases, in most cases, increases the hold time, except, again with ISO, if we choose 90% of enclosure height, adding agent actually defeats our purpose and decreases hold time, but that's because we continue to raise the minimum protected height, which is something I don't agree with, but that's the way the standard is written. Always lowering the protected height for descending interface increases retention time. So this slide talks about our training course, which you have 3 levels. The first one is for authorities, fire protection engineers, and for all testers as well, an orientation. And level 2 is the basics for testers, and level 3 is advanced testers, which includes below ceiling leakage area measurement, and we encourage people to take all 3 levels if they're testing. Watch our website under webinars. You'll see our schedule up there as to what's up and coming, and thank you for your attention.